Time for another lesson. Section 2.2, separable equations. So this is our fourth section now that we've covered, and we're finally going to learn how to solve a specific type of differential equation. This is the easiest type, separable equations, right? So what this means in spirit is that you can separate x and y, right? If you can separate x and y across the equal sign from each other, or in some way, then you can just integrate both sides to find the solution. And sometimes we don't even have to do the separation part. Sometimes we can just do the integration part. And that's this first kind of problem. Solutions via integration. If someone hands you a differential equation of the form dy dx equals some function of the independent variable, right? Dy dx equals some function of the independent variable. In this case, all you have to do to solve for y is to integrate this dx and integrate this dx. And then when you integrate both sides dx, this side will become y, and it will equal whatever function of x is over here. So if you ever get derivative y with respect to x is equal to just a function of x, then the easiest thing to do is just to integrate both sides dx. Let's look at an example. So here we have dy dx equals some function of x, right? No y's. There are no y's on the right-hand side. In that case, we just integrate the left-hand side dx, integrate the right-hand side dx. The integral of a derivative is just the function itself. And to integrate this function, you just do, well, the power rule on this guy. The integral of a constant is just x. And this is a u substitution, or I guess you'd call it the inverse chain rule, right? When you integrate e to the 2x, if you were to take a derivative of e to the 2x, you would get 2e to the 2x. But since we're integrating, we get 1/2 e to the 2x, right? You divide by the power. And then you have to be careful. Always, always, always tack on the constant. So in Calculus 1, for about a week, there was a big fuss made about tacking on the constant at the end when you do an indefinite integral. It's incredibly important that you do that every time in differential equations, because what we want is a family of solutions often. And if they give you some initial condition, like say they told you that y of 0 was 1, you'd want to be able to evaluate that. And the way to do that is by adding on this constant plus c. Right? This plus c gives you a one parameter family of solutions. So if you take nothing else away here, it's whenever there's indefinite integrals, always, always, always the plus c comes at the end. Okay, this is the solution to this differential equation. Sorry, this is a family of solutions to this differential equation. If you were to plug in this for y right here, right? Plug y in right here, you'd get 1 plus e to the 2x equals 1 plus e to the 2x. That's how easy it is. So that's the easiest type of separable equation, when there is no separation that has to be done. But in general, a first-order differential equation is separable if it has this exact form. Dy dx equals some function of x multiplied by some function of y. It's very important that they're multiplied together. Very important that they're multiplied together. Again, I'll say it one more time. Dy dx equals g of x, some function of x, times some function of only y's. And it can be, well, let's just look at some examples. Let's say if these things are separable or not. First one. Dy dx equals y squared x e to the 3x plus 4y. Right now, it's not in the form of some function of x times some function of y. But with a little algebra, we can separate this exponential, right? Remember that addition in the exponent becomes multiplication in the basis. Addition in the exponent, multiplication in the basis. We can separate this exponent up into e to the 3x times e to the 4y. And now if we look, we have this right here is a function of x, and this right here is a function of y, and they're being multiplied together. And if we write it like this, it's very clear, right? This is g of x, and this is h of y. So this is a separable equation. This is a separable equation. Next example, dy dx equals y plus sine x. There's no way to write this as a product of a function of x times a function of y, right? The addition is no good. It has to be multiplication between the two terms. Here's another one, kind of sneaky, right? dy dx equals 1 plus y. I'm not seeing any x's here, but that's totally okay. I can take g of x to be the function 1, and h of y to be the function 1 plus y, right? And in that case, we get this is equal to g of x times h of y. So this is a separable equation. Very separable. How do you solve a separable equation? Well, the easiest way to describe it is to divide and then integrate. Like I said at the beginning of this section, we're going to put all the y's on one side and all the x's on the other. And often what it looks like is something times y, something involving y dy equals something involving x dx. But it might not be multiplied per se, it could be divided. Right? So let's look at how we do it. So we start with dy dx equals g of x times h of y, right? We start with a separable equation. And the idea is we're going to move the h of y across and move the dx across. Normally, we treat dy dx like a function, but in this case, we can treat it like a fraction. Like dy is like a bit of y, and dx is like a bit of x. Right? A little y and a little x. And we can move those independently of each other if we allow ourselves to. So I'm going to move this h of y across, and I'm going to multiply the dx across. And this is what I get. Right? 1 over hy dy equals g of x dx. And now this differential dy and this differential dx are separate. I can just plop an integral sign out front and integrate both sides. Right? Integrate both sides. So now I get the integral of 1 over hy dy equals the integral of gx dx. And when I take the antiderivatives here, I'm going to get some function of y equals some function of x plus c. I should mention, we did this earlier and I didn't even mention it, but technically when you anti-differentiate over here, when you take the indefinite integral, you also get a plus c on this side. But you can just take that constant and add it into this constant. You only need 1 plus c in the whole equation, is what I'm trying to say. So technically both this side gives you a plus c and this side gives you a plus c, but we can lump this plus c into that one. Right, we can lump the constant of integration over here into this constant of integration. So we really only need 1 constant of integration. How about an example? Here's a differential equation for us. Already separated out, kind of nice, but not exactly what we need, right? We need all the y's to be together and all the x's to be together, but right now there's an x with a y and a y with an x. So instead what we're going to do is we're going to move this term across the equal sign, right? And then, in order to put the y's on this side and the x's on the other, we're going to just cross multiply or divide both sides by 1 plus x and y. And we get down to this equation. Now, this side, only y's. This side, only x. That's separated. That's separated. We can now integrate both sides. Integrate both sides. That's what we do. We integrate both sides. Now the integral of 1 over y is the natural log of the absolute value of y. The integral of 1 over 1 plus x, technically you can do a u sub, right? U equals 1 plus x. And then du is going to be 1. So you get 1 over u du, and you integrate that, you get natural log absolute value u, and then you resub in u equals 1 plus x. That's how we get here. And then, like we said earlier, you get a constant of integration on both sides, but those can be condensed into one single constant of integration. So we get the natural log of y, absolute value y, equals the natural log of absolute value 1 plus x plus c. And we can take exponentials on both sides. And we have to be careful, but we're taking the exponential of this whole right-hand side. When you raise both sides to the e, you really have to treat each side of the equal sign like a single term when you raise it to the e. Right, so we take e to this whole side, and we take e to this whole side. That's how you exponentiate both sides of the equation. On this side, the e and the natural log cancel, and we're just left with absolute value y. On the other side, we've got e to the natural log of stuff plus c. And we can do our little trick here, and addition in the exponent becomes multiplication in the basis, right? So this becomes e to the natural log of stuff times e to the c. So we get absolute value y equals absolute value 1 plus x times e to the c. And if you've forgotten how to get rid of absolute values, you do that by putting a plus minus. Right? You do that by putting a plus minus. So when you drop absolute values on all sides, you just add a plus minus on one side. Right? Because if absolute value of y equals absolute value of x, that means that either y equals x or y equals negative x. Right? Those are the only two options. So in order to drop absolute value bars, you just add a plus minus. And then we can be a little sneaky here. Since c is arbitrary, right? C is an arbitrary number. That means that e to the c is an arbitrary number, right? So since c can be any number, that means e to the c can be any number. And since e to the c can be any number, so can plus minus e to the c. That's just a single constant, right? We can lump this e to the c and the plus minus together into a constant, right? Because if you take plus or minus e to some constant, you just get a constant. So really, all we're saying is that y is equal to some constant times 1 plus x. And that is the solution to the differential equation, right? Given this differential equation, it has a family of solutions, and here they are. This is all of them for different choices of c. Okay, let's do a few more examples. What if we start with dy dx equals negative x over y, with the initial condition that y at 4 is equal to negative 3. And we saw this in section 1.1, and we said that, we gave a, what was it called? An implicit solution, right? Gave an implicit solution in section 1.1. But it's in fact separable, and we can solve this exactly, right? We don't need to rely on someone handing us the solution because we can find it ourselves. How do we deal with separable equations? We put, I should mention that this is separable because it's equal to, this is equal to negative x times 1 over y, right? Which is a function of x times a function of y, right? So this thing really is separable because it's negative x times 1 over y. Negative x times 1 over y. So how do we deal with a separable equation? We put the y's to one side and the x's to the other, right? Take the y's across, take the x's across. So we get y dy equals negative x dx. integrate both sides. Integral 1/2 y squared equals negative 1/2 x squared plus a constant of integration. A little cleanup, we can move this term across and we get x squared over 2 plus y squared over 2 equals a constant. And if I multiply through everywhere by 2, right, I can clear out these denominators and I'm just left with another constant, right? Because 2c, when c is an arbitrary constant, is just another arbitrary constant. So I get the solutions to this equation look like x squared plus y squared equals a constant. And now I can invoke my initial condition, y of 4 equals negative 3, y of 4 equals negative 3, plug that in here to find the exact constant that gives the exact solution to this differential equation. Right, so technically there's an infinite family of solutions to this differential equation. But by specifying an initial condition, I can pick out a specific solution. Right, a specific solution. So that's what I'm going to do. I'm going to use the fact that y of 4 equals negative 3, which means x equals 4 and y equals negative 3. And I'm going to plug that into my equation. And I get 4 squared plus negative 3 squared equals constant, which means 25 equals my constant. So the solution to this differential equation passing through this point is the circle of radius 5 centered at the origin. The circle of radius 5 centered at the origin. Now we got to be careful sometimes when we're dividing, right? As you know, or as you should know, right, dividing by 0 is a no-no. Right? Dividing by 0 is a no-no. And sometimes you can lose solutions when you divide and start canceling. Right, so let's look at this guy. Let's look at this example. dy dx equals y squared minus 4. Again, this is 1 times y squared minus 4, which is g of x times h of y. This is separable. This is separable. So what am I going to do? I'm going to move all the y term across, and I'm going to move the dx term across. So I get 1 over y squared minus 4 dy equals dx. Probably my least favorite, but we're going to be using it a lot, techniques, as far as integration is concerned, is the method of partial fractions. If you've forgotten how to do partial fractions, now's the time to refresh yourself, okay? It's going to be coming up a lot. It's going to come up a lot. It's pretty easy to integrate 1, right? We know how to do that. This side, on the other hand, hard to integrate. But thankfully, we can use the method of the partial fractions. How do we do the method of partial fractions? Well, you look at y squared minus 4, and you factor it, right, into y minus 2, y plus 2. And our goal is to split this fraction into an addition of these two fractions, right? You factor the denominator, and you put the factors in the denominator as the denominators of the two partial fractions, right? And since we don't know exactly what a and b are, it's our job to find them, right? It's our job to find them. In order to solve for a and b here, we're going to multiply through by the denominators, by this denominator on the left-hand side, right? Multiply through by the denominator on the left-hand side to cancel out all of the denominators, right? And since y squared minus 4 is equal to y minus 2 times y plus 2, when I multiply this fraction by y squared minus 4, I cancel the y minus 2, and I'm left with the factor of y plus 2. And the same thing over here. When I multiply through by y squared minus 4, I cancel the y plus 2, and I'm left with the y minus 2. Right, so after multiplying through by this denominator, I'm left with this equation. 1 equals a times y minus 2 plus b times y plus 2, y minus 2. And now I'm going to do what's called picking convenient numbers. Right? Choose convenient numbers. And here the convenient numbers are the ones that make either this term or this term equal to 0. Right? If I pick y equals -2, this whole term will disappear. And I'll have one unknown in one equation, and I can solve that. If I pick y equals 2, I'll lose this whole term, and I'll have one equation and one unknown, and I can solve that. So that's exactly what I do, right? I pick y equals 2, and I'm left with, after I pick y equals 2, this term goes away, and I'm left with 1 equals a times 2 plus 2, which is 1 equals 4a, which means a equals 1/4. Alright, so that's exactly where I got this number. And similarly, if I pick y equals -2, I get b equals -1/4. So now, I've effectively solved for a and b here, and I've split this fraction up. Right? I've split this fraction up into linear pieces. So, 1 over y squared minus 4 is really 1/4 over y minus 2 plus, plus -1/4 over y plus 2. And now we can go back to my integration, right? Go back to my integration. I'm going to substitute that partial fractional decomposition I just found for this term, right? If you remember, it was 1/4 y minus 2 minus 1/4 y plus 2. Now each of these is a linear term on bottom, and I can do that by u sub. And this is just a 1 dx, which integrates to bx, right? So when I integrate both sides, I get 1/4 natural log y minus 2 minus 1/4 natural log of y plus 2 equals x plus c. And by working the power of the logarithm rules, right, this is log rules, addition on the outside, subtraction on the outside becomes division on the inside. Right, so I can factor out this 1/4 from both terms, and I'm left with natural log minus natural log, and when you subtract on the outside, you divide on the inside. Now I'm going to clear out the 1/4 by multiplying over by 4, right? So now I've got just the natural log of stuff equals 4x plus 4c, and again, 4c is just a constant again. A constant times a constant is a constant, right? And then I'm going to take both sides to the e, just like I did before, right? Just like I did before, raise both sides to the e power. The e and the natural log cancel, right? I can drop these absolute values and get a plus minus, and that's exactly what I do. So I get y minus 2 over y plus 2 equals plus minus e to the stuff. And then I'm going to do the same trick I did before. This is plus minus e to the 4x, e to the c, e to the 4x, e to the c. And I can combine these two terms together, because this is plus minus e to an arbitrary constant, which itself is just an arbitrary constant. So this trick gets used a lot, I should say, and we'll keep using it, where plus minus e to the c just becomes c. Okay? And by doing a little magic here, I guess I should write out what I did. I'm solving this for y, right? I'm solving this for y. How do you do that? Well, you take y minus 2, you set it equal to c e to the 4x times y plus 2. And then you FOIL it out, y minus 2 equals c e to the 4xy plus 2c e to the 4x. And then you group the y's on one side, group the constants on the other. You get y minus c e to the 4xy equals 2 plus 2c e to the 4x. Whoops, I lost it. And then you just divide by the stuff in front of the y, right? And that gives you this. Now, we should remember that we started with dy dx equals y squared minus 4. And that there are two solutions to this, right? Y equals plus minus 2. y equals plus minus 2 are two solutions, two constant solutions to this. Y equals 2 lives inside of this family of solutions, right? If I put c equals 0, that implies that y equals 2 times 1 over 1, right? Which is 2. So y equals plus 2 is in this infinite family. However, y equals minus 2 is not in this infinite family, even though it is a solution to this, right? If I plug in y equals minus 2 into here, right, what do I get? The derivative of minus 2 is 0, and this is 4 minus 4 on this side, which is 0. So 0 equals 0, which is correct. So y equals negative 2 is a solution. However, there's no way to make this side equal negative 2. This will never equal negative 2. We call this a singular solution to the differential equation, right? These are special solutions called singular solutions. And you have to be careful sometimes, because you'll lose them. Okay, that's the end of section 2.2, separable equations. They all follow the same basic roadmap. Some things to remember, final parting words if you made it this far into the video. You have to separate over multiplication, not addition. When you integrate both sides, you'll get a constant of integration from both sides, but you can lump those into one single constant of integration, right? So 1 plus c is enough. And last but not least, remember, when you integrate 1 over y, or whatever, when you integrate 1 over something, you get natural log absolute value. Please remember your exponent rules when it comes to the exponential functions. Dropping the absolute value y to get a plus minus is not a big deal because it can be absorbed into the constant. And last but not least, partial fractions, right? Partial fractional decomposition is going to be your friend. It's going to be your friend for a while. Okay.